will be telling us about Gauss Garbled circuit garbling and Gauss two-party computation.
Okay, so today I will be talking on circuit garbling, one of the most fundamental concept in multi-party computation, and then we will talk about Gauss two-party computation protocol based on Gauss Garbled circuit. So here is the road map. So we will start with Gauss Millionaire's problem, the famous problem that triggered the fundamental area of secure multi-party computation. Then we will move on and we will discuss the generic secure two-party computation or 2PC problem. So Gauss Millionaire's problem is actually a special case of generic secure two-party computation problem. We will briefly see the security goal, but you probably would have already seen a detailed discussion on the security definition in Manoj's talk. Once we are done with the security goal, then we will discuss Gauss proposal for the two-party computation protocol, which is based on the fundamental concept called Garbled circuit and oblivious transfer. So in this talk, we are going to elaborate on Garbled circuits, and we will take oblivious transfer as a black box and use it in our protocol, in the Gauss protocol. In my next lecture tomorrow, we will talk in details about the second primitive, which is oblivious transfer. And in the end, we will trace the fabulous journey of Garbled circuits a bit, and then we will conclude with some very interesting open questions in the domain. Okay. So here goes the problem, the Gauss Millionaire problem. So this is introduced by Turing Award winner Andrew Yao back in 1982 in his foundational work called Protocols for Secure Computation. And here is the problem. So to be consistent with the pictures in the slide, we can as well call it as Gauss billionaires problem instead of millionaires. So here is the problem. So the problem is that we have two billionaires, right, and they would like to know who is richer between them, but without disclosing their exact asset to each other. Okay. So of course, if they make their asset public or let the other guy know, then both of them can compute who is richer between them. So the challenge is that they want to find out who is richer between them, but without disclosing the exact asset they have. Okay. Generalizing the problem that you have seen in the previous slide, what we get is a secure two-party computation problem. So here we have two parties. They do not trust each other, and they have their private inputs x and y, right. Now they want to compute a function f on their private inputs x and y, and at the end they would like to know just f of x comma y and nothing beyond, and all that is implied from this function output, which is f of x comma y, but nothing beyond that. Okay. Now the problem of secure two-party computation can be further generalized in terms of number of parties. So we can, instead of two parties, we can make it n parties, and what we get is actually secure multi-party computation, where we have n parties. N can be two or more, okay, and the parties do not trust each other. The distrust is modeled by having an adversary who is a centralized adversary, and who can corrupt some of these parties. Okay. Now every party Pi has some private input xi, and there is a commonly agreed function, n input function f, that they want to compute on their private inputs. So the goal is that they want to compute this function f of x1, x2 up to xn. They would like to know the function output, right, correctly, but with the constraint that nothing beyond the function output must be leaked in that process. Now there is a humongous amount of applications of MPC. Some of them you have already seen probably. So if the applications, I mean it starts, ranges of applications are there, starting from preventing satellite collision, then e-voting, then electronic election, outsourcing, privacy preserving machine learning, then privacy preserving data analytics, and so on and so forth. So what is common among all the problems is that in all of them you need data privacy and data usability or computing on the data at the same time. So you want to keep your data private, but at the same time you want to do some computation on your private data. In fact, MPC is since it is it captures almost anything in cryptography, it is arguably called as the holy grail problem of cryptography. Anyway, so in this talk our goal is to discuss two-party computation, which is a special case of MPC where the number of parties are restricted to 2. Okay. So I'll just, I think you have already seen a number of applications of it, but I'll just give one example, and with that I'll conclude the application part of it. So think of two hospitals in the country, right? AIIMS and Apollo Hospital, for instance. So they have their own medical records of their patients, okay? And let's say they want to together compute some statistics on their private database. So these databases cannot be made public, or they cannot be disclosed to some other hospital, okay? So they are binded by law. So these hospitals, they cannot make it public. So if they want to find out some statistics, some interesting statistics on their joint database, right, then they have to, then MPC or 2PC can be a solution for it. Okay, now that we are motivated, so let us ask the question how we can solve the problem of 2PC. So the problem can be very straightforwardly handled if you can trust someone. So if you have some trusted third party, for instance, who you can trust, then what can the parties do is they can simply, let's say that these parties are connected to the trusted third party through a secure channel, okay, each one of them. Then they can send across their private inputs to the trusted guy. The trusted guy can compute the function f on x and y, and then he can hand over the output to the individual parties. Okay, very simple. Since the channels are private, everything is fine. So the parties gets to know only the function output and all that is implied from it, but nothing beyond it. Okay. But so this is called ideal world secure two-party computation protocol, but TTPs exist only in fairy tales. So we are in the practical world where we don't have such TTPs to help us out. So we still have to find a way out, and that's exactly 2PC protocols does. So it suggests to distribute our trust. So we'll have a protocol that is run between the parties themselves, and at the end they would know only the function output and nothing else. In a sense, this protocol is going to simulate the effect of a trusted third party between them. Okay. So this is basically the goal of any 2PC protocol. We want to have a protocol that would emulate the effect of having a TTP between the two parties. Okay. So with that, let us now, so now we have seen the security goal. We will now proceed to see the protocol proposed by Yao, which is based on Garbled circuit approach. Okay. So what Yao suggests is that we do for solving the two-party computation problem, we do secure function evaluation. So we will evaluate the function securely, which is in a sense same as secure circuit evaluation. So there is a connection between function and circuit, and here is that you get it from complexity theory, that for any function that is polynomially computable, right, there is a circuit representation for it. Okay. So it can be Boolean or arithmetic, both actually, but for Yau's solution we need the Boolean circuit representation of the function. So any polynomially computable function you have, for that you have a corresponding Boolean circuit representation, right. And so basically the circuit is nothing but DAG, right, with varieties of gates. For instance, so for if it is a Boolean circuit, then you have this AND gate, OR gate, NOT gate, and so on and so forth. Okay. So this is from here the two-party protocols gets its generality, that it can compute, it can handle any function in general. So you take any general function, for that you have a corresponding circuit representation, which we are going to evaluate in a secure way. So I will elaborate what do we mean by secure circuit evaluation in next few slides. But before that, let me just quickly demonstrate you that we can actually find circuit representation for polynomially computable functions. So here I have taken the example that we have got from Yau's millennial problem. So remember that there the function that we wanted to compute is nothing but greater than equal to, right. So two guys, they have their own private asset and then they want to find out who is richer between them. So essentially we wanted to compute greater than equal to function for the x and y inputs that the individual parties had, right. So I am going to show you very quickly how you can get a circuit representation of this greater than equal to function. So let us assume that x and y are L bit non-negative integers, right. These are the bit representations of x and y. Now assume that we have a bit comparator, right. So it compares two bits, xi and yi, and then it outputs C. So it has it takes another input which is Ci. So Ci is given as 1, just to indicate that xi, I mean with the assumption that xi is greater than equal to yi, and it outputs Ci plus 1. So this circuit basically implements this logic. So Ci plus 1, this one, will be 1 if and only if this bit xi is greater than yi, that is one case, or these two bits are equal and Ci equal to 1. Okay. It's clear what the Ci plus 1 computes, right. Now you can easily go back and find out the representation of Ci plus 1 in terms of xi, yi and Ci. It is actually this. So this is there is nothing, no magic about it. You can go back and solve the truth table and you can come up with this expression. So as you can see that this Ci plus 1 can be represented in terms of xi, yi and Ci, and essentially you need 3 XOR gates and 2 AND gates, that is it. Now I can use this bit comparator to design a Boolean circuit for this function, which is the greater than equal to. Do you see it already? So you actually need L copies of this this circuit to come up with the circuit for greater than equal to. So this is what you do. So the first bit comparator takes x1, y1 as the input, and C1 is set to 1. So this C2 will tell you whether so far x is so far in the sense that whether x1 is greater than equal to y1 or not. You can easily check that C2 will be equal to 1 if and only if x1 is greater than equal to y1. And then to the next bit comparator you feed C2, x2 and y2, so on and so forth, and finally you get CL plus 1, right, and you can see that x, this the whole x is greater than equal to 1 if and only if the final bit, which is CL plus 1, if this is equal to 1. So x will be greater than equal to 1 if and only if C of L plus 1 is equal to 1. So, this is the Boolean circuit representation of the greater than equal to function. So, this is just a demonstration, but in principle any a polynomially computable function f can be represented by a Boolean circuit. Okay. Now, we will move forward. Now, the idea that Yao proposed is the following. He says that do secure circuit evaluation. What that means is that the parties will jointly evaluate the circuit securely, right, so that only the final outcome of the circuit will be known, but no intermediate values will be leaked, including the inputs. Okay. And the way he suggested to do is through circuit garbling. Okay. So, what does circuit garbling do and what is the goal of doing it? So, they are stated as follows. So, in circuit garbling, we first garble or encode the circuit, right, and then we encode the input to the circuit, then we evaluate the encoded circuit on the encoded input to get encoded output, right. And then finally, if you disclose the decoding information, with that you can just find out the output, but nothing else. Okay. So, a circuit is encoded or garbled and then input to the circuit is encoded, then the circuit, the encoded or the garbled circuit is evaluated on an encoded input to get encoded output. Finally, when we give some decoding information, that gives or leaks just the output and nothing else. Now, what is the goal of garbling? So, the goal of garbling is that nothing beyond the function output should be or the circuit output should be leaked. So, that includes that we preserve the privacy of the input that is fed to the circuit. Secondly, we do not leak any intermediate gate output values, right. And lastly, we will also not leak output if the decoding information is withheld. So, if I give you the decoding information, with that you can decode the function output or the circuit output, and that is all you can do. Okay. So, intuitively this is what we do in circuit garbling and this is what we want to achieve. So, of course, I have not stated these properties formally, these are stated in informal level, but I think it makes sense to you, right. So, with this goal, now we will see how we can garble circuit. So, to make the presentation easy, I have taken a very simple circuit. So, this is a 3 input circuit, it takes A, B and C as the input and it has just 2 gates. This is an AND gate and this is an OR gate, that is all. Okay. Now, if you want to, let us say, evaluate this circuit so you want to evaluate this circuit on clear with these inputs, let us say. So, A takes 0 value, B takes value 1 and C takes 0. So, how would you go about evaluating the circuit on clear? So, first of all, you will have some topological ordering of your circuit, right. So, for instance, for this gate it is very simple. So, you can start with this gate for instance. Okay. So, you have 0 and 0, you look up the truth table, right. So, you have to go to the second row. So, it is for 0 and 1 and you should get 0 as the output. So, that means that you can this output where of this gate gets 0 value for these 2 inputs. Now, with 0 and 0 you again look up the table, this time for OR gate, and it corresponds to the first row and you get 0 as the final output. So, if you want to evaluate this circuit on clear, let us say on this specific inputs, then this is how you go about doing it, right. Now, my first goal is to garble this circuit so that I can evaluate the garbled circuit in a encoded way. So, the first step of the garbling is to garble the wires, and then I will garble the gates. Okay. So, to garble the wires, we will associate 2 keys with every wire. So, let us start with this wire. So, we associate 2 keys which are, this is very important, which are identically looking. So, although they are not looking identical, so this is for your advantage, I have given 2 different colors, but we are associating 2 keys which are identical looking. One key is given the meaning 0, the other key is given the meaning 1. So, for simplicity we can say the key that is associated with 0, we call it as left key, and the other key is called as the right key, right. So, they are identical, that means that if I would have associated the meaning, right, and then you do not know anything about it, and I give you just one key out of those 2, you will not be able to tell apart which bit value it corresponds to, whether it corresponds to 0 or it corresponds to 1, that you will not be able to tell apart. Okay. So, we do that with every wire in the circuit. We do it with this, we do it with this wire and this wire. That is it. So, we are done with garbling the wires. Next, we have to garble the gates. So, for that we will associate 4 boxes with every gate. So, let us start with this gate. So, we have associated 4 gates corresponding to 4 rows of the truth table. Okay. Now, in the first box, so the first box corresponds to the first row. So, we basically want to encode the output of that row in this encode or lock in this box. So, look at this row. So, the output is 0. So, we want to hide the left key of the output wire in the first box. The second row, the output is 0. So, we are again going to put the left key of the output wire in this, and same for the third row, but for the last one the output is 1, right. So, we will put the right key of the output wire in the last box. Okay. Then we are going to lock these boxes, right. Now, each of this box will be locked with 2 keys. Okay. Now, which keys we are going to use to lock these boxes is very interesting. Okay. So, the first box is locked with the left key of the input wire A and the left key of the input wire B. So, what we want to capture here is that if someone has 0 and 0 on these 2 wires, right, then he should be able to open this box, and similarly for the other boxes. So, if someone has left key for A and the right key for B, then he should be able to open this box. So, this box we are going to lock with left key of A and the right key of B. Okay, so this is how I okay. So, these 2 keys are used to lock the first box. Then the left key and the right key here is used to lock the second box. Then the right key on A and the left key on B is used to lock the third box, and lastly the right key on A and B are used to lock the last box. Okay. So, you see the intention, right. So, if someone has these 2 keys, that means it has 1 and 1, then he should be able to open this box, and in this box we have kept the key which corresponds to 1 in the output wire. So, he will be getting that particular key. So, that is the intuition that we capture here. Okay, and in a very similar way you would construct 4 locked boxes, doubly locked boxes for the second gate, right, and then we are done. And this is what, so the pack of 4 boxes for every gate, if you put together all such 4 cipher or 4 boxes, what you get is the garbled circuit. So, my garbled circuit means the set of these 4 boxes for every gate in the circuit. Okay. Now, so we have seen how to evaluate a circuit on clear. We will now see how we can evaluate a garbled circuit. So, this is the garbled circuit on encoded input. So, let us take the same example. So, let us say you want to evaluate this circuit with 0 on the where A. The encoding of that input here will be nothing but the left key corresponding to where A. So, why do I say that this is an encoding? Because by seeing this key, as I said that they are identical looking. So, for everywhere we have associated 2 identical looking keys. So, just by seeing this key, right, no one will be able to tell apart whether it corresponds to 0 or 1. Okay. So, in the right side we are doing a garbled circuit evaluation, whereas on the left side we are doing evaluation of a circuit on clear. Okay. Okay, so given 0, you here you get the left key. Then if your input where B takes value 1 there, then you will be giving out the right key here. And similarly, if C has got the value 0, then here you are going to give the evaluator a left key. Okay. Okay, now with these 2 keys, the evaluator of the garbled circuit is going to do the following. So, he has got 2 keys. With that, he is going to try to open the 4 boxes that are available to him, and definitely one box will open, right? And which one is that? So, if it is 0 and 0, these 2 keys correspond to 0 and 1 respectively, then basically the evaluator can open the second box. Okay. So, he will open the second box, and inside he will find a key, right, and that key he will associate with the output where of that gate, right. So, he got this key. Now, he has got both the keys for the input wires of this gate. With that, he is again going to try to open the 4 boxes corresponding to this gate. Okay, so going back, so this is basically, you can see that this is this part of it is actually simulating as if on the clear, as if you have 0 and 1 and you have looked up the table and you have got the value 0 here, right. And then now coming back to this domain, so now you are again trying to open, and you will be able to open the first box, yes, and then you will get the left key. This is same as if in the clear world they are looking up the table and then they have got the output bit 0. But here you have got just the key, so by seeing the key you would not know whether it corresponds to 0 or 1. So, we need to give out some information which we call as the decoding information. Right. Once we give that, then this guy who is evaluating this will be able to tell what output he has got. So, the decoding information can be nothing but the 2 keys that you had associated with the output wire. Okay. So, if I give these 2 keys, then this guy can check whether this key is equal to this or this, and then based on that he would know whether it is 0 or 1, but that is all he is going to know. Okay. So, yeah, so by comparing he would finally get to know whether it is 0 or not. Okay, so do you think everything is okay? Here I am able to garble, and I am able to satisfy the goal that we had set, that is nothing beyond the output is licked. Do you find some problem in it? So, I have, yeah.
The intermediates are also revealed.
How?
So, like when A and B compute, then the output of the AND gate is also a key which is revealed.
Yeah, so how do you get to know the intermediate gate values?
So, that's a key which is publicly known.
Exactly. So right now I have not done anything with the boxes. So the boxes are as per the truth table. So let's say you have got some key here and some key here, and with that you have opened, let's say, the second box. Then you can tell apart, I mean you can easily, you know that this box actually corresponds to the second row, which means the key that you have got here is definitely the left key, and the key that you have got over here is the right key, and the key that you have got here by opening this is the left key corresponding to the output where. So you need to do something. So the solution is that we just need to do shuffling, random shuffling of the boxes, the locked boxes that you have created. So once you create the 4 locked boxes, you just shuffle it, you randomly permute the boxes, right, and then after shuffling what you get, that is actually called your garbled circuit. So this 4 shuffled ciphertext boxes corresponding to the gates gives you your garbled circuit. Okay. So then you cannot tell the meaning of the input keys or the output keys that you have got. Okay. So far so good. So now I am going to replace the physical keys and boxes with cryptographic mechanisms. Okay. So what we are going to use is a symmetric key encryption or SKE, which has 3 algorithms: GEN, the key generation algorithm, which is represented by G, and then encryption algorithm, which is represented by E, and then we have the decryption algorithm, which is represented by D. So this is what we are going to do. So instead of picking 2 physical keys, you are going to pick 2 random keys, 2 keys uniformly at random from the key space of the secret key encryption, and that you are going to associate with your let us say the first way, and this you keep on doing for all the wires in your circuit. So that is the first step. Okay, associate 2 random looking keys, 2 keys uniformly random from the key space of the secret key encryption. Okay. So we do this with the second wire and so on and so forth. Fine. Now you know how the doubly locked boxes would look like. So again we will have 4 ciphertext corresponding to the 4 rows of the truth table. The first ciphertext we are going to encrypt the left key, because 0 is the output here, using the left key of A and the left key of B, right, double encryption. Then in the second encryption we are going to hide K3 of 0 again, but this time with the left key of A and the right key of B. Then for the third ciphertext we are going to hide again K3 of 0, because 0 is the output here, and this time we are encrypting it using the right key on A and the left key on B. And the last ciphertext will hide the right key, which is K3 of 1, using the right key and the right key on A and B respectively. Okay. So this is how we are going to create the 4 ciphertext, and as we have mentioned, we have to shuffle it, and finally what you get is 4 ciphertext, but you don't know which ciphertext has gone where. In a similar way, you have to construct 4 ciphertext and you shuffle it, and finally this pack of 4 ciphertext for every gate gives you the garbled circuit. Okay, so again let us do the evaluation on clear in the left and in the garbled domain in the right side. So you have 0 here, the corresponding to that the evaluator of a garbled circuit would be given the left key of A. You have 1 here on B, so the evaluator in this domain gets the right key. Here a C takes value 0, so here you are going to give the left key, right. Now in this domain you can see that Yeah, so now with these two keys again you have to do some trial and error. You are going to try out the decrypting the 4 ciphertext at hand. Now something can go wrong here which was not there in the physical key and lock domain, because there if you would have locked with some particular key, that key itself you have to use to open it. If you use some other key, that lock is not going to open for you. But something can go wrong here in the secret key domain. So we have usually the SKEs, the secret key encryptions that we see. If you encrypt some message with a key, right, and later you try to decrypt with a different key, it will probably give you something. It of course not, it's not the same message that you have encrypted, but something else. But here how do the evaluator know that whether that is what is intended or not, right? What do you do? What do you do? So we need some extra properties from our secret key encryption. Okay. So yeah, so this is basically the 4 ciphertext in some order hidden in this 4 ciphertext. So this is the format. So if we have a pair of keys here, right, we don't know which ciphertext to decrypt from this 4. So what we will do is we will try to decrypt all the ciphertext. But what if in all the cases you get something, right? So all the decryption gives you some value. So which value is to go for? And this can be solved by having a special secret key encryption which has special correctness property. And this is what actually we need from our SKE. So we will say that our SKE has this special correctness if for 2 distinct keys K1 and K2, encryption under K1 will result in bot when you decrypt under K2, and this happens with overwhelming probability. So if you encrypt something with key K1 and later try to decrypt it with using some other key K2, then very likely you are going to fail. You will not get any valid message, you will get bot, and that way you will get to know that this is probably not the ciphertext that I wanted to decrypt. Okay. Yeah, so mathematically this is what I want, and fortunately we have such SKEs. We can plug those kind of SKEs in and then the problem will be sorted out. Okay. So now we can complete it, because now we know that with this pair of keys you are going to open just one box out of those 4 boxes, the rest will not open. With very high probability you will get bot when you try to open other 3 boxes. So you know what value to go forward with. Okay, so that way you get this key K30, and with these 2 keys again you will try out all possibilities, but yes.
In decryption, here the message space is only binary, right? Either 0 or 1.
No, so the decryption will give you the key. So the ciphertext are hiding it is one of the 2 keys that you are hiding in those ciphertext. It's not binary. Okay.
What is meant by a bot?
Bot means, so the decryption algorithm will fail. So you will see somehow nothing is coming out from the domain of the messages. So probably it will be clear when you see an instantiation of such things, but for now you can assume that we have such SKEs where you will know whether the decryption has resulted in the correct decrypted value or not.
So you get a key that basically doesn't belong to the key space.
So we don't get anything. We can somehow detect that the encryption has been done using some other key. You can detect that. Yeah.
Possible keys. So if I decrypt all the 4 possible encrypted texts, so wouldn't they should only correspond to one of those 2 keys. So true. Why do we
No,
need
but
that special key?
you don't get these keys. You are actually, you got, so in the input layer you have got one key corresponding to the inputs on which you want to evaluate the garbled circuit. You have no idea about these things. You are going to get it by decrypting these things. Yeah, so you cannot verify that. All you get is the 4 things, these 4 ciphertexts for every gate. Okay, so done. So finally, in order to decrypt the output value, in order to know the final output, we have to give the decoding information, and the decoding information is nothing but the pair of keys that you had associated with your output wire. In this case, these two keys. So once you get this key, then you can check which key it is, and then you can find out that this key actually corresponds to 0, which means that your circuit output is 0. Okay. So do you see that we have already kind of achieved what we aimed for, that we want to garble a circuit, we want to encode a circuit, and then we want to encode its input, and we want to evaluate the encoded or the garbled circuit using encoded input, and finally we will get the encoded output. And by giving out the decoding information, all I enable the garbled circuit evaluator is to get the final output value and nothing else. So the input information remains secret. None of the intermediate gate output values are leaked. Only the final thing is leaked. The final output is leaked. So to ensure that, so we need some security property from the underlying secret key encryption. For instance, so we want that a bad evaluator should have no information about what the 3 unopened ciphertexts contain. So he will be able to open one of those 4 ciphertexts. So remaining 3 unopened ones should not give any information. I mean, what value they contain, what values are hidden in those 3 ciphertexts should not be leaked to the evaluator. Okay. For instance, if he can guess, for instance, that the 3 unopened ciphertexts encrypts the same value. So he doesn't actually need to know what exactly is encrypted in those unopened ones. If he can somehow guess that they are same, that itself is enough to leak a lot of information. So think of an AND gate. Okay, and let's say that the evaluator has opened the box corresponding to the right key of the output wire. Okay, so the 3 remaining unopened ones, they would have encrypted the left key. Okay, so if he can somehow guess that those 3 unopened ones contains the same thing, that itself is enough to tell him the meaning of the key that he has got. He definitely knows that for an AND gate, in 3 of the ciphertext, it will be the left key which will be encrypted, in the last one it will be the right key. So if he has got the right, so whatever he gets is basically the right key, meaning that it has the meaning 1.
So this implies that for each run we need to build this circuit from scratch, as in
Ciphertext, new keys.
Yes, everything you are using fresh randomness. Yeah.
I mean, it's inefficient in some sense.
Speaking randomness is that is true, but so I'm not. But if you have a good enough machine, a laptop, I think this is not a bad thing to do.
but this it is not linear circuit, so that is a
Yes. Okay, so yeah, so basically this is something that we want to prevent the bad evaluator to do. That is, he should not be able to even guess whether the remaining 3 unopened ciphertext contain the same message or not. Even that should not be allowed. So this is captured by introducing a game. So if you are not familiar with the language of experiment or games for defining security, you can skip this part, but you probably have got the intuitive idea that I have explained so far. So basically what we want is that the adversary, who is the bad evaluator here, right, so he knows 2 of the keys, right, for each wire. So, we allow the adversary here to pick two keys K0 and K1. These two keys basically signifies the two keys that he would know. For instance, for this where he would know this key and this key. So, he gets to, that is why he gets to pick those keys, the adversary. So, he gives those keys to the challenger, and he also gives two pairs of 3 messages. So, this actually corresponds to the 3 messages corresponding to the unopened ciphertext. Now, this challenger is going to pick 2 keys which he is going to keep it with himself, he is not going to leak it to the adversary, and these 2 keys actually correspond to the 2 keys for instance here this one and this one, which the adversary has no information about. Okay. And now this challenger is going to pick a bit that will tell him that which 3 messages he is going to encrypt and give a challenge to the adversary. So, if the bit is 0, then he is going to pick this 3 message. If bit is 1, then he is going to pick this 3 message, and then he is going to create 3 ciphertext in the following way. The first ciphertext encrypts XB using K0 from here and K1 prime from here. So, notice that one key is known to him, the other key is not known to him because it is picked by the challenger. The second one is created this way. So, here this key is the unknown one and this key is the known one, and the last one is encrypting the third message, which is ZV, but this time both the keys are actually unknown to the adversary. Do you see that this 3 ciphertext actually correspond to the 3 unopened ciphertext? Because for the 3 unopened ciphertext here, the adversary will be missing either one key or both keys, right. So, that exactly is captured here. So, now if I create, if the challenger creates this 3 ciphertext, right, and gives it to the adversary, and if the adversary is not able to tell apart whether the challenger has picked this set of 3 messages to encrypt or this set of 3 messages to encrypt here, then we should be fine. Because what it captures is that even though the adversary, who is actually a bad evaluator here, even though he gets to know one pair of keys, which is this, let us say this and this, and he does not know the other pair, right, he has no way of telling apart whether 2 sets of messages, which out of these 2 sets of messages are encrypted. Where notice that these 2 sets are also picked by the adversary. We give the adversary to choose the 3 messages, a pair of 3 messages from which we want to encrypt, still he is not able to tell apart. It is a very strong property. So, we call it as, so if no polynomial time adversary is able to win in this game, meaning that he is able to correctly guess the bit B, that is which set of 3 messages are picked and they are encrypted in this 3 ciphertext, then we say that we are fine, meaning that our scheme is fine. So, if for a secret key encryption there exists no PPT adversary which can guess this bit with probability which is exponentially, which is overwhelmingly more than half. Of course, with half probability anyone can guess it. It is just a bit, so anyone can, you do not need any fancy mechanism, you just can guess, flip a coin and you can answer it, you will be right with half probability. So, the thing is that if there is no PPT adversary who can win this game with probability which is overwhelmingly more than half, then we are fine. And we say that the secret key encryption has this property called chosen double ciphertext security. So, basically, yeah. Oh, chosen, yeah, you're right. I think, yeah, this is, yeah, chosen double plain text security. Okay. So, finally, this is what we want. So, we want a secret symmetric or secret key encryption SKE with special correctness and chosen double plain text security. In fact, it has been shown that this particular security can be obtained from a CPS security. So, if your scheme satisfies CPS security, then it also satisfies this notion. Okay. Good. So, that is it. So, we have seen how to garble a circuit and how to evaluate a garbled circuit on encoded input and how to get an encoded output at the end, and how by giving a decoding information we can just leak the output and nothing else. Okay. So, with that we are ready to discuss the Yau's two-party computation protocol, but before that we need another primitive which is called oblivious transfer. So, we are going to take it as a black box. So, I am going to just define it in a very simple way, and then in tomorrow's lecture we are going to elaborate on this particular primitive. So, in an oblivious transfer primitive, you have two parties, a sender and the receiver. In its basic form, the sender has two inputs, let us say M0 and M1, and the receiver has a bit R, okay, which indicates which out of these two messages he wants. So, this indicates which out of these two messages he wants. So, if it is a bit, right. So, if it is 0, then that means that he wants, okay, so we can call it as M0 and M1. So, if it is 0, that means that he wants M0, and if this bit is 1, that means that he wants M1. Okay. Now, the oblivious transfer protocol allows the sender to send the message of receiver's choice while hiding the input of the choice bit of the receiver on one hand and hiding the other message of the sender on the other. So, this guy will not know what R is, and on the other hand the receiver will not know what M of 1 minus R is. So, his choice is MR, and that is all he will know. He will have no information about the other message of the sender. So, this is what oblivious transfer does. So, we are going to represent the oblivious transfer with this box, which has two input ports in the left for the sender. So, the sender can input two messages here. Oh, sorry. So, this is this arrow will be the other way around. So, and then it has one input port here where the receiver can input its bit, and it has an output port here through which the output, that is the chosen input of the receiver, will come out. Okay. So, you can think the oblivious transfer as this box, simple box. Okay. So, we are going to use this primitive for Yau's two-party computation protocol. So, in Yau's two-party computation protocol, as the name suggests, we have two parties, P0 and P1. One party is going to act as garbled circuit constructor. So, one guy will construct the garbled circuit, whereas the other guy, he is going to evaluate that circuit. So, he is going to act as the garbled circuit evaluator. Okay. So, the first guy has input, let us say X, and the second guy has input Y, and at the end they would like to compute f of xy. So, first let us take a very simple example. So, what they want to compute is an AND gate, let us say. So, that this x is P0's input and y is P1's input, and they want to find out what is x dot y, the product of the two bits. That is all they want to find out. Okay. So, let us discuss this first, and then we can generalize to it for any general function f. Okay. So, let us take this interesting evaluation where P0's input is actually 0, which means that x takes 0 value and y also takes 0 value. That means that at the end they will have 0 as the output. Okay. Since the first guy has 0 and at the end he will get 0, right. So, he should have no information about the input of the other guy, because if his input is 0, no matter what input P1 has, whether it is 0 or 1, the output should be 0. So, just by seeing the output he should not know anything about the input of P1, and the same holds for P1 too, because P1's input is 0 2, right. So, if P1 also has 0 as the input, he should not know whether the input of P0 is 0 or 1. So, when we discuss the protocol, we will see that these properties are they hold good. Okay. Okay, since this is the AND function, and they together want to compute it, fine. So, and this guy acts as the Garbled circuit constructor. So, what he does is he takes the circuit, which is nothing but a plain AND gate here in this case, and remember how the garbling works. So, we have to associate a pair of identical looking keys with everywhere, and with the help of the keys we are going to create 4 ciphertext, right. So, those 4 ciphertext, and then you do shuffling and all that is there. Now, finally, this is what you get, 4 ciphertext. Now, the Garbled circuit construction is done. Now, he is going to send the following to the other party. So, he is going to send the Garbled circuit, which is nothing but this pack of 4 ciphertext, right, and plus the decoding information, which will allow this guy to learn the function output, and the decoding information is nothing but the pair of output keys in this case. Now, since this guy is acting as the Garbled circuit evaluator, he needs to know the encoded inputs. In this case, it will be the key corresponding to 0, which is this guy's input, and also the key corresponding to 0 for the where y, right. So, when he gets both the keys, only then he can start evaluating. He will have the full encoded input, and only then he can start evaluating. So, since this guy has garbled himself, he has constructed the Garbled circuit himself, and he wants to evaluate this gate on 0, right, he knows which key to send. So, for this where he would simply send this key, because this is the one which correspond to 0, and this is the encoded input of the 0. So, he is going to send K1 of 0, the left key on this where, because that correspond to 0. Now, so in order to start evaluating, as I said, this guy has to get the key corresponding to 0 2, corresponding to where y, yeah. How does he get? He cannot simply give his input to this guy, right, then it reveals the input. So, what do we do? Do you have any suggestion? Oblivious transfer. So, we are going to use one oblivious transfer where the Garbled circuit constructor, that is P0, is going to input these 2 keys, and this guy is going to input, so the arrows are in the wrong order. So, he is going to input his input 0 as the choice bit, and correspondingly he will get the key corresponding to his input. So, in this case, since his input is 0, he is going to get the left key, right. Okay, so, he puts 0 here, and then he will get the left key, fine. So, he has got the left key on this where, and he has also got the left key from here. Of course, he does not know whether they are left or right. So, he has got this one, and just by seeing this he will not know what bit it corresponds to. That comes from the fact that the keys are identical looking. And for this, so for this he anyway knows. So, fine, now with these 2 keys he goes ahead and he evaluates the circuit, and then one of the boxes will open because of the special correctness property, and then you are going to get K30, he is going to get K30. Now, he has got the decoding information, so he uses that, and then he finds out the meaning, which is that means that the output is actually 0, because this one matches with this key, and that is it. He sends back the output to this guy, and then you can see that this person will also not know about the input of this of P1, and why is that? Do you know the reason why P0 will not know anything about the input of P1. What prevents him from getting that information? Comes from the security of the oblivious transfer, right. So, oblivious transfer ensures that the sender, so this guy is acting as a sender for this oblivious transfer, he will have absolutely no information about the choice bit of the receiver. So, the choice bit here is nothing but the input of P1. So, it comes from the security of the oblivious transfer. Yeah.
If the first person had selected x equals 1 and in the end he gets to know that then he knows that the second person has an input.
Right. So, that is a very interesting question. So, what I said is that in 2PC you will get to know the output and all that is implied from the output. So, in this case it is implied from the output. If your input is 1 and you get 0 as the output itself implies that the other guy's input is 0. So, that is not a, yeah. So, the function output itself, if it leaks something, that we can't prevent even by having a protocol. Okay. So, that is it. So, that is the specific instantiation for a particular function, which is the AND function. You can easily generalize it for any function that you want. So, now this guy can have a long input which consists of, let us say, k bits, and similarly here k bits, and the function is known. So, this guy constructs a Garbled circuit for this big circuit, and then he sends the Garbled circuit plus the decoding information, and along with that he also sends the keys for his input, right. And then they run a set of OTs. In this case it is k, because the number of input bits of P1 is k. So, we run k OTs, and then this guy will get the corresponding keys corresponding to his input bits, and that is it. With that he will evaluate the Garbled circuit, decode it, get the output, finally he sends across the final output back to the Garbled circuit constructor, and both of them now knows the function output. That is it. That is it. So, we are almost there. So, I just want to tell you something about some recent progresses that has been done in the context of garbling. So, first of all, there is a very nice technique which is called point and permute, right, which removes the need of this special correctness property that we wanted from our SKE. Okay, so it's a very simple and clean trick which you can use, and once you use that trick, you actually no longer need that special correctness property. Any CPS secure encryption scheme will be fine. Okay, and also with this technique you do not need to go and try out decrypting all the 4 ciphertext. It will actually point you to a particular ciphertext without leaking all that we have discussed, and you can just decrypt that particular ciphertext and go ahead with the decrypted key. Okay. Then there had been lot of interest in bringing down the number of ciphertext corresponding to the Garbled circuits, because as you Garbled gates. So, as you have seen in the Yau's 2-party protocol, you basically have to send across the entire Garbled circuit to the other guy. So, if you can reduce the number of ciphertext that you need to garble a gate, then it will be very good. For instance, if you can probably garble with 2 ciphertext, right. So, that will bring down the communication cost by a huge amount, by half, for instance. So, these techniques are called garble row reduction. So, we had long back we had a procedure that can give that can garble an AND gate using 3 ciphertext instead of 4. Okay. Then there are very interesting set of works which actually tells us how to garble AND gates with 2 ciphertext instead of 4. Okay. And it has been also proved that 2 is kind of the minimum that you can achieve. So, you cannot go beyond 2. Then actually instead of, so the ciphertext are actually k bit long at least, where k is the security parameter. We can break that bound and we can actually do with 4 bits to garble an AND gate, but this is for a specific class of circuits. So, these are called form-like circuits, where the fan out of every gate is 1. So, a particular gate output, any gate output cannot go to multiple gate input, it cannot act as input to many gates. So, that is the restriction you have. If you have that kind of circuit, then you can actually garble a gate with just 4 bits. Okay. And then we have result, which says that you actually do not need any ciphertext to garble a gate, you can do it with 0 bits, but there are some restrictions. So, first of all, this also applies to form-like circuits, and secondly, so the technique that I have discussed so far, there we assume that the keys are of equal length. So, they are of size which is a security parameter.
Are these equally secure as k-bit?
Yeah, almost yes. So, there will be some small differences, but yes. And here the second thing is that the key length will be dependent on the circuit depth. Okay. Right now what we discussed, it is independent of the circuit depth. So, everywhere for all wires we are choosing keys which are of length, the security parameter. Then we have techniques for improving the XOR gates. So, these are very special kind of gates. Okay. So, we have technique which we call as free XOR or flexor. So, the motivation here is to garble the XOR gates with 0 ciphertext, and also the cost of garbling as well as cost of evaluating will be 0, in the sense that you will not need any cryptographic operations. All you need is some bit XORs, cheap, which are very cheap.
In XOR, anyways, the other person's bit is revealed. If I know my bit and if I know the output, then the other person's bit is revealed regardless. So, do we really?
No, but then this is if it is an intermediate gate, then.
So, even then, if I know my
Yeah, so it is. So yeah. So some intuition that it's a special kind of gate. We exploit that, and then it can be done with 0 ciphertext. And then you don't need any cryptographic operation. It can be done with just plain XOR operations, which are very, very cheap. And lastly, these are some very interesting paper that came up in 2012. So, that elevated the garble circuit from technique to primitive, and then they define very nice set of features which we call as privacy, obliviousness, authenticity and verifiability. And since then people have started working on garble circuits alone. So, irrespective of the application, so they try to give new garble circuits, which of course would try to optimize in terms of the number of ciphertext or computation of garbler and the constructor and so on and so forth. Then we have seen some very interesting application of garble circuits in the domain of for instance zero knowledge, then outsourcing computation. So, we have already seen how garble circuit can be used for two-party computation and also multi-party computation. So, these are apart from that. So, we see that garble circuit can also be used in zero knowledge and outsourcing of computation. Okay. Yeah, so for zero knowledge specifically and also for outsourcing of computation, we can actually do with special kind of garble circuits which are called privacy free garble circuits. So, basically here you would know the meaning of the keys. What we want to hide is the key which you are not supposed to get in the output where. So, let us say you have some inputs and at the end you are supposed to get one key, right, by so this is privacy free, but it has this authenticity property, which means that you should not know the other key, meaning that which corresponds to the other bit, I mean which you are not supposed to get. So, you have got one particular keys corresponding to one input, you should get the output key which corresponds to that output alone, you should not be able to get the other thing. Okay, so that is all, and yeah, so we are actually running a very interesting study group or reading group just on garbling. If you are interested, stay tuned to this page, so you will find a lot of interesting references which are relevant to garbling. So, if you want, you can follow, and yeah, that is it. And I just want to update you about some of the recent things that we have done, just in one line. So, we have got something which is very interesting, which we if we are given formulaic circuits and we want to construct circuits which are privacy free, that means we need only authenticity. We saw that how we can do with 0 ciphertext. So, basically our Garbled circuit is a null string, we do not have anything. This is very interesting. And we also studied zero knowledge from Garbled circuits. We studied the round complexity of zero knowledge. So, these are all works that are under submission. Will not elaborate much, and we also have constructed some non-interactive secure computation from Garbled circuits. Okay, so that is all I wanted to say, and it's fine, right? Okay. Thank you. So, I want to say that I am totally exhausted. I got up at 4 in the morning, and then I have a very small kid. So, I couldn't even sleep in the last night, and I am still awake. I am just surprised that I am still awake. And you can probably catch, so all the authors, the works that I have mentioned in my previous slide. So, all the authors are here. So, Pratik, Yash and Divya. So, they are yeah, so they are all working on garbling. So, if you want to know more about garbling, you should catch one of us. Yeah, they are, some of them are here for the workshop.
Do let me know, because we have like short slots for student presentations. So send me a mail if you are not yet there.
Maybe this is, I do not know if this is too late for them, I do not know. Anyway, so if you have questions, you can still ask me. I think I will be fine since I have. Yeah.
All technique depends upon bots. Bots.
The bots?
You said in between.
Yeah, the decoding should fail.
Yes.
For correctness, you need that.
Yes. Can you clarify what value should be there so that?
So you will, so basically you will be able to, so when you run the decoding algorithm, you will know that nothing is coming out of it. So you will not get any, what basically represents that you will not get anything.
But like you said, the point in terminal,
Yeah.
it feels that you don't need, so that's the way to go.
So we already know a technique where you can bypass the need of special correctness. You just need any SK that has CTS, that provides CTS.
Is there any value? Is there range which tells that if value is not in between this range, then this must be rejected?
No, nothing of such kind we need now. So any SK scheme that has security is good enough for us. With that point and permute, which I have not discussed.
So in the point and permute technique, so as you say that there is maybe some technique that will point out to one particular ciphertext which we will decrypt. But what prevents an active adversary from checking all the decryption? So that holds only for passive guarantees, right? So what I mean to say is that point and permute only is for passive security, right?
Right. So no. So the point and permute technique will allow you to go and find out the particular ciphertext that you need to open.
Correct.
So you have one pair of keys, right? So anyway, you cannot open the other three ciphertexts.
I can try to open.
You can try, but you know that you will not get anything. Corresponding keys.
Even in passive, that prevents the basically from doing other things that it will. So Even for passive, it's an important consideration whether you can get something by doing decryption you are not asked to. Coordinate coordinate just makes it more efficient to.
And one more question, the double ciphertext security, so does it, so as you said, like from a CPA we can compile that to a double CPA security. I mean,
You can prove that if a scheme has CPA security, then the scheme also has.
Yeah, so does it hold for symmetric encryption or in general for all public key crypto also?
So this is, at least this has been proven in the context of SKE. I am not sure if it has been. So there was, first of all, no need of doing that. So I don't think anyone has ever tried, because we need SKE for the Garbled circuit. So people have tried to. Okay.